Hey guys, in this question we're going to be finding the linear approximation for a function. So to get started, we need our formula for a linear approximation. And I've gone ahead and written that out right over here. And as you can see, we're going to have to first evaluate the function and then compute partial derivatives with respect to x, y, and z to be able to get our final answer. So let's get started. So the first thing is plugging in our values or our point into the function. So let's go ahead and do that. So I'm going to make this gray. Okay, perfect. So for f of a comma b comma c equals, this is our function right over here. So I'm going to say f where a is 6, b is 3, and c is also 6. So 6, comma 3, comma 6 equals the square root of 6 squared plus 3 squared plus 6 squared. I plug this into my calculator, I'm going to get that the function, or this point, equals root 81 or 9. Okay, now that I have this value, I can move on to my partial derivatives. So for this part right here, this is the partial derivative of the function f with respect to x. So I'm going to write this over here, partial derivative with respect to x. So f of x equals, so I'm going to rewrite this function as x squared plus y squared plus z squared to the power of 1/2. So we're going to have 1/2 times 2x, because that's the derivative, and then I'm going to write x squared plus y squared plus z squared minus 1/2. So if I simplify this, I'm going to get that f of x, or the partial derivative of x with respect to x, is x over the square root of x squared plus y squared plus z squared. Okay, now let's move on to the partial derivative with respect to y. So to obtain that, we're going to be doing the same thing as above. So at the partial derivative with respect to y, and I'm going to take the partial derivative to y, and then x squared plus y squared plus z squared, and then negative 1/2. And that comes out to be y over square root of x squared plus y squared plus z squared. And that's our partial derivative with respect to y. Just gonna color code them so it's easier for later. And then our last one is z, which is right over here. So partial derivative with respect to z is going to be 1/2 times 2z times x squared plus y squared plus z squared to the power of negative 1/2. And if I simplify that, I'm going to get z over the square root of x squared plus y squared plus z squared. Okay. Now that we have all our partial derivatives, we can simply plug into our formula. Okay, so going back to our formula, we know that this number right here, or this should be 9. So this part is 9. I know that this part is right here. So, and then we also know that all the partial derivatives are below, so right here and right here. So to obtain a number though, I'm gonna have to plug in the point 6, 3, 6 into each one of these expressions to get a value for the partial derivatives. Okay, so I'm gonna go ahead and do that. So this is gonna be x over, or x equals 6. So I'm gonna write 6 over the square root of 6 squared plus 3 squared plus 6 squared. So I know this part is 9. So 6 divided by 9 is going to give me 2 over 3 equals 2 over 3. And then for this part, I'm going to have 3 over the same thing. So it's going to be 6 squared plus 3 squared plus 6 squared. So I know that is 9 again right here. The denominator is 9. So therefore, it has to be 1 over 3. And then lastly, we have the same thing. So I'm just going to copy this over here. Okay. And that's what we have. So we have our values for the partial derivative. So we can plug those numbers in over here. Okay. And then for A, B, C, that's given in the question. So let's go ahead and finish this linear approximation. So the linear approximation for 6, 3, 6 for this function equals 9, because that's the first part. Next, we have our partial derivative with respect to x, which is plus 2 over 3. Next, we have x minus a, and a is 6. So times x minus 6 plus 1 over 3, because that's our partial derivative with respect to y, times y minus b, and our b value is 3, times y minus 3, plus our partial derivative with respect to z, times z minus our c value, which is 6 over here. Okay. Now we want to estimate, we want to make a linear approximation, and that's an estimate. So instead of choosing the points to plug them back in, so 6, 3, 6, I'm going to choose points close to those values. So let's say for A, I'm going to choose 6.022. For B, I'm going to choose 2.992. And then for C, I'm probably going to choose 5.9, let's do 7.2. Again, you can choose any set of values. We're just trying to get numbers that are super close to 636. Okay. Now moving on, I'm going to plug, so I'm going to delete this part, and I'm going to write what I have above. So the reason we're doing that is because we're trying to find an estimate. And also, if we plug in 6 here, 3 here, and then 6 here, all we're going to get is 9, because the zeros are going to multiply out, and then we're going to be left with our constant 9. So we have 6.022, 0.022, comma, 2.992, 2.992, comma, with this. And lastly, we have 5.972. Okay, plugging these values into x, y, and z, we're going to get 9 plus 2 over 3 times 6.022 minus 6 plus 1 over 3 times y, or this is 2.992 minus 3 plus 2 over 3 times 5.972 minus 6. And if I plug this into my calculator, real quick, I'm gonna get that this is approximately, so L of x comma y comma z, I'm gonna get that this whole thing is approximately 8.9933, which is pretty close to our actual value. So in summary, linear approximation uses tangent plane to estimate nearby values. It's kind of like saying, instead of recalculating the whole curve, let's use the flat line that's almost the same near the point we know. Thanks for watching.